Hello and welcome to my Lab 2 video presentation. The purpose of this lab was to develop a computational model to illustrate how charge tapes interact with one another when treated as lines of charge, and estimate the magnitude of charge for one of these tapes. This presentation will consist of an introduction, a statement of my major assumptions and key physics concepts used, my experimental procedure, the development of my computational model and its output, and finally a conclusion and quick discussion of my results. My overall results are displayed below. I found the magnitude of charge to equal 3.73 times 10 to the negative 8th coulombs, and the magnitude of electric force to equal 0.001923 newtons. My first major assumption was to assume the charge of each tape is uniformly distributed, which allows us to model each tape as a line of charge. Secondly, we must assume that each tape has approximately the same magnitude of charge. The three physics concepts used during this lab are the electric field due to a point charge, the principle of superposition, and Newton's second law of motion. The experimental procedure for Lab 2 is essentially the same as Lab 1. We start by creating a base tape, and from that base tape creating charged U-tapes, which we will use to observe interactions between the charged tapes and other objects. In particular, we're interested in how two charged U-tapes interact with one another when they're placed one on top of the other. If we measure the distance between these two charged U-tapes, we can use that information to calculate the magnitude of charge on a given piece of tape. On the right, you can see my calculations and lab notes for this experiment. I started by recording the length of the top U-tape and the distance between two charged tapes to be 19.6 centimeters and 5.1 centimeters respectively. The only calculation that we needed to do for this lab was to calculate the weight force, so I started by drawing a free body diagram of the top piece of tape. Since there's no change in momentum, we know that the sum of the forces in the y direction must equal 0, and thus the electric force is equal to the weight force. The weight force we can calculate by determining the mass of the tape and multiplying that mass times the gravitational constant g. Given the linear density of a charged piece of tape and the length of the tape in meters, we find that the mass of the tape is 1.96 times 10 to the negative 4th kilograms. From this, we determine that the weight force is equal in magnitude to 1.923 times 10 to the negative 3 newtons, and thus the electric force has the same magnitude. Here you can see my computational model. The purpose of this model is to estimate the magnitude of charge for a U-tape if both tapes are treated as line charges. We can represent these lines of charge in GlowScript using the line charge function given in the starter lab code. The line charge function will generate n spheres along an axis, each with a differential charge dq proportional to the size of n, which I completed in lines 54 and 55. Then we can measure the electric field and electric force each differential piece of tape 2 is exerting on each differential piece of tape 1 by iteration, shown in lines 85 through 106, and use of the E-field function defined in lines 19 through 25. If we sum all of these differential electric forces, we will find a total electric force proportional to the magnitude of total charge defined in line 11. Since we know that the electric force must be equal in magnitude to the constant gravitational force, we can modulate the magnitude of total charge until we find that the forces are equal, which will reveal the estimated magnitude of charge for a U-tape. Displayed here is the output of my computational model. The top red line represents the upper U-tape, and each green arrow represents the differential electric field of a piece of tape 1 caused by each piece of tape 2. Notice that the differential electric field vectors seem to fan out, and most contain a non-y component. If we use superposition to sum each of these differential field vectors, we will find that every non-y component will cancel, leaving an electric field solely in the y direction, resulting in a perfect cancellation of the gravitational force. This electric force is illustrated by a white arrow pointing up, while the gravitational force vector is yellow and pointing down. The text output of my model confirms that the magnitude of each force is the same to 4 significant digits when the magnitude of charge is equal to 3.73 times 10 to the negative 8th coulombs. For a piece of tape 19.6 centimeters in length, treated as a uniformly distributed line of charge, the magnitude of total charge on the tape will equal 3.73 times 10 to the negative 8th coulombs based on my computational model. This corresponds to an electric force of magnitude 0.001923 newtons, which is equal and opposite in direction to the gravitational force. Thanks for watching.